Hello, my name is Parv Joshi, and today I will be teaching you how to do regression and classification in R. So for regression, I will be talking about simple linear regression, multiple linear regression, interaction terms and transformations, and also variable selection and penalized regression. For classification, I'll be covering logistic regression, decision tree classification, and random forest. So let's get started. Okay, so let's get started. So I'm expecting you to already have RStudio. If you do not, you can just go to Google, type download R first, and then you can get it from here. And after you install R, you should install RStudio because that is the IDE we'll be working in. So once you open it, this is how it will look like. And over here is where you actually make your script. And here, this is the console where everything you run comes in here. And you can also run one-line codes in here, which is not going to be saved. So if you want to save your code, you want to write it on the upper side. Over here, this is the environment. So every variable you define, global or local, whatever it is, it will come in over here. And it also has history on what you've done, your connections and tutorials. And over here, you can see your plots, you can see your files, packages. There is help, which is really helpful for looking at documentation. And there is a viewer option that is mostly for interactive plots and things like that. So first things first, let's actually try to import some of our data. So I've created this folder, which is in my drive called R tutorial regression and classification. And I want to pick up this data file, which is in CSV format, which is something most of us would work on in real life. So R actually has a built-in function to read a CSV file called read.csv. However, we need to make sure that that file is in our current working directory. So if you don't know what our current working directory is, we could type in get wd, and it will tell you what my current directory is. Once you open RStudio, it is mostly going to be your documents folder or something like that. So I do not want this to be my working directory because my files are stored in a local place, which I want to use throughout this video. So the way to set your new working directory is using set wd. And inside that, you put in quotes and you put in the exact path of your directory. For me, I'm going to copy this path from here and paste it here. But there is actually a problem because these backslashes here, they actually represent special characters. So there are two ways to solve this. I could make these double backslashes. So also, if you're running Mac, then you probably don't have this issue because you already have slashes instead of backslashes. So this is one way I could set my working directory. Now this thing has run, so there is no error. So my working directory has changed. Alternative way of doing that is replacing these with slashes. And this is actually very similar to the way Python does it. Also, once you have your directory, you can read your file, but I want to show you another way of checking your working directory and setting it. So in this bottom page, mostly by default, you're going to be in the plots. But if you go to files and if you go to more, you'll get many options. Like first one is go to working directory. And it goes to my working directory. And then if you want to change your working directory, if you see over here, there's like small 3 dots. And if you click on that, you can choose your directory. So this is right now in my documents. I want to go to my drive, where again I'll choose this folder and say open, and this actually just opens it. It does not set as your working directory. So and I go to more over here and set as working directory, and that actually runs the same code which I did before. So this is one way of doing it if you don't want to learn setwd and getwd. But also one thing with R scripts is that you have to use the setwd function every time you open your R project or R file, and you always have to run this code. So it's better to have it in your script. And that also has potential problems that sometimes you change your directory, you rename your files or something like that, or you just move it to another place. In that situation, it is going to become a little difficult setting your working directory every time. So for that, there is actually a new, not a new way, but it is a more efficient way of doing this is called R projects, where you just create an R project, and every time you open your RStudio, you're by default in the same directory, and you do not need to like set your working directory every time. So I'm gonna make a new project. You go to File, New Project, and you have several options. It could be like an existing directory or something you when you make it on yourself, or it could be a version control, a Git repo. So I'm going to go to a current directory, and this is where I want to store all my files. So I'm going to create a project here. So this is going to take me to that project now. And if I go to this file, you see this file has been, it's got our history and our project user file, and also this our tutorial regression and classification.r proj file, which means this is now a project, so I do not have to use the setwd and things like that. So I also have lost my current file which I was working on because I didn't save it, and I don't think there is need for that because I will be creating a new file, and this time I'm going to create on our markdown file. So what we had before was an R script. Now I'm creating an R markdown file. It is also called RMD, and I'm going to give it a title, and I am the author. My name is Parv, and there are default output formats. You can choose between HTML, PDF, and Word. I honestly like the PDF one pretty nice, but the thing with PDF is it requires LaTeX, and also when you're trying to export it to PDF, it will tell you how exactly to do that. It's through RStudio as well. You do not have to install LaTeX externally. But for our purposes, HTML is an easy way, a better way of presenting this. So I'll be sticking with HTML right now. And what you see here is the RMD file. It has a title, author, date, output. And this is similar to how LaTeX does it. Like if you have seen a LaTeX document before, in the starting, it will have a title, the author, the date, and things like that. So this is how it is similar to that. And however, when it comes to this file, it is actually a combination of R and Markdown, and that's why it's called RMD. And if you see this thing, this is actually a code chunk. So anything that goes inside this is our code, and everything that's outside is Markdown. So we do not type in LaTeX in this. We type it in Markdown, and Markdown is converted to LaTeX, and that's how this works. So if you see in Markdown, if you've used it before, you know this is like a heading. Like if one this thing will be like a heading, one hashtag heading, heading 1, and then if you have 2, it's going to be heading 2. So yeah, this is how it will work, and this is the text, the normal text in it, and then you can have multiple codes. And if you see like after this R, what you have is setup. This is actually the name of the code chunk, just to make it more organized. And there's a lot of things you can modify for a code chunk, and for that there's a good resource. If you go to Google, just type RMD cheat sheet, and the first link is going to be the one here. It tells you all about R, like how to use the syntax. See the header 1, header 2 is here. how it looks like, how to type in block codes, math, and even pictures, and even the different types of output formats it allows you to do it in, and how to do inline code chunks, display options. These are the different display options. Like if you, in the code chunk, if you go back here, we have include equals false. So instead of include, if you had like error equals false, it will not show you errors in the output of your program, which is really good if you're creating a report, a formal report. You don't want like unnecessary errors to be there, or even warnings. I think there is something for warnings. Yes, warning equals false. We'll set all the warnings to be. It won't allow the warnings to be in your output. So this is a very good way of formatting it. And this is an incredible resource. I'll attach the link to this in the description. So let's go back here, and we actually did not need the code that's already there by default. So I'm going to start in this document, but before I start, I want to save this. So it's going to be this thing, and I'll say our tutorial. So your file name does not have to be the same as your title. It could be different. I am using the same title in here. And let's get started. So basically this video, I aim to go over a bit of regression and classification using R. However, before I do that, I want to teach you how to read data and a little bit of data pre-processing, which I wouldn't go in detail about it. So let's get started. I'll create a heading here called reading data. And now if you want to create a code chunk, there is a shortcut to do this. If you're a Windows user, it is Control-Alt-I. If you click that, you get this code chunk. For Mac, I believe it is Command-Options-I, and that will give you the same code chunk. And you can rename this. I would say read data. And then I don't think I need anything of those warning equals false or anything right now, so I'll just give it a name like this. But if you're giving something like warning equals false, you have to have a comma after the title, and then it will say, it will give you all the options you want. So say warning equals F. Warning equals F is equivalent to using warning equals false. So in R, if you write T, it means true, or you could just write true. Both are the same thing. UE. And basically, writing T or F is shorter than writing true or false, but I prefer writing the entire word true and false. It's actually all capitals, so uppercase. And the reason I do that is because it is more readable, writing true and false explicitly, just rather than just writing T or F. But it really depends on your use case. So so let's start by importing the data. As I mentioned, there is built-in function called read.csv. In this, what you do is you just write in the name of your file. So I want to import this data.csv file. I'm gonna copy this name here and paste it in here. But I have to assign this to a name. So that's what we'll be referring in this. So I'll say dataset equals read.csv data.csv. And also in R, you can just use, most people tend up using this symbol, and you can use equal to instead of that. It doesn't really matter. I tend to go with equal to because that's like a more global way of defining variables or data sets, especially in other languages like Python. So it's more readable for a person who doesn't know R. So I would say for running this, of course, you can run a line. You can run this. Okay, so for this entire code chunk, you can run the entire chunk. It could be many lines of code altogether. But the shortcut for running one line in R is Control Enter or Command Enter if you're using a Mac. And if you do this, you can see that you inside your data, you have this thing data set with 10 observations and 4 variables. We'll get into that. So before I do so, I wanted to let you know that R runs line by line. So, and that's how I'm mostly going to run all my code. And this is one way of doing it. This is Control Enter is one way of doing it. And if you see there's this run option, which actually allows you to select your lines, and there's a lot of options. If you want to run multiple lines, you can select all the lines together and then press Control Enter. The reason you might want to do that is because you do not want to run all the code, but parts of the code. And yeah, that's about it. And also I wanted to tell you about this thing, which we'll actually do sometime later. So it actually runs all the code chunks about this one, does not run this one. So suppose you wanted to run some code chunk, but it required you to run a previous code which you had in another chunk, then this would be a really helpful tool to do it. So now let's look at this data set we have. If we click on this, like anywhere, so there are actually two ways of doing this. You can click on the blue thing and it will tell you what all columns are there in this data set and what is the column type. For example, the first column is country. It has a character, it is a character variable, so it's like strings, and it has like the first observation is France, then Spain, then Germany, then Spain. Then age is integer, salary is integer, it's like the first observation, the second observation, third observation. Then purchase is also character, it's no, yes, no, no, that's how it is. And if you click on this data set or somewhere else, but not on the blue arrow there, then it's going to open it in a new tab and it's actually going to show you in a table format. So this is really nice. Now coming to this data set specific, this is actually not real data. It is a made up data, like really small data set, just for illustration purposes. So yes, this is how it looks like. And also there's one thing to note in R, we start our indexing from 1 to 10 instead of 0 to 9 if you have 10 observations. And if you want to know more about the data set, I mean, over here, of course, this tells you there's like 10 rows and 4 columns. So that's how it works. The alternate ways of doing the same things, let's say you wanted to see this thing as, you wanted to write it as a code, you don't want to see it over here. So the way you would do is str of data set, and that will give you the same thing. So str stands for structure. It tells you about the structure of this data frame, and data.frame, this is like the type of the variable data set. It is a data frame. What like we all know data frames, like it's usually abbreviated as df. So yeah, also if you wanted to view this table, you will write view, and over here the v is uppercase. That's what you have to keep in mind. And I would put in data set here, and it's going to open the same thing. So that's the code for that. So usually I would prefer not writing these codes, or even if I'm writing, I will remove them once I've used it, because if I'm outputting the entire file, and if the data set is too long, it's going to be like pages and pages of the data set, which no one wants to read. They actually want to read our report, not want to see the entire data set in our final version. So I'm going to remove that, or maybe I would just comment it out. The way of commenting this is using hashtags. So basically, even if you try to run these, it's not going to show you anything. It's just a comment. So yeah, I'll just keep it as commented over here. So this is how you would read data if it's an external data set. When it comes to a built-in data set within R, we will go over that in future examples. So this is how you would read your data set. And since we already have this data set over here, we want to try something else using the data. So let's try data pre-processing. So let's say data preprocessing. So as I told you, I do not want to get deep into data preprocessing, but I will teach you like some of the techniques in here. Now let's say if you go to this data set, we actually do not know what this data set means. We do not have its documentation. What we know is there is a country column that's usually just France, Spain, and Germany, nothing else. Then there is ages, and there is salary, and then there is purchase that says yes or no. So, so this, although this was a made-up data set, I know what it's supposed to mean, what it's, why it's supposed to be used. So actually, this is of a company that operates in 3 regions. That's France, Spain, and Germany, and it has 10 customers. And their salaries are given in here, and the company wants to know that like the product they made, did this person buy it or not? If they have bought it, it will say yes, otherwise it will say no. And they want to run an analysis to check if purchase actually depends on the country they're from, the age of the customer, or their salary. And this is why this data set was initially made, although it is not real data. So if you look closely, the first thing is we have these NAs, which looks different from the other ones because it's italics, then it's a gray color, not white one. So that is because it is a missing value. This is how R tells you that it is missing value. Now, if you have missing values, there are many ways of getting away with that. There is removing the entire row, or most people just go for some kind of imputation. It's mostly the mean or the median imputation. So let me show you how the mean imputation works. So I would just say mean imputation. And what I would say is, first you need to choose which column you want to do the mean imputation. Let's do for both age and salary. Both these NAs will be gone. So for age, now to take out that age column, we need to specify to R like which data set you're getting it from. Over here we have only one data set, but still you have to mention. The way of doing it is you write your data frame name, that's data set in this case, and then you put a $sign, and then it'll give you all the options, what all columns it has, and you choose which one you want, the age. And what I would say is you want to do a mean imputation. So you can do this by an if-else condition. That would be like if the value is NA, then you replace it with the mean of all the other values in age. So if you want to do a simple if-else statement in R, there is a function called if-else. So one word, if-else, and then put the parentheses. And then if you see over here, it tells us if-else test yes, no. So basically, this has 3 arguments. The first argument is the condition, the if condition. The second condition is second argument is that if the condition holds true, what happens? And the third argument is if it holds false, what happens? So now you want to check if a condition is that if there is an NA. So I would say there's a function for checking that called is.NA. So this function checks if there is a missing value. Now if is.NA, and you want to do this for the age variable again. So is.NA of data set $age. This is your condition. Now you want to write your second argument, which is if it is NA, then what do you do? So the way of doing that is using the AVE function. So it is a function where you can do a mean imputation. So, but you have to specify, but it's not necessarily that you use the mean imputation. You can do median imputation by that as well, but you have to specify the function which you're using, either the mean or the median or something else. So the first thing you want to put in here is the data set of age itself, because that's the column you want to find the mean of. And the second argument is function, f1 equals, and I'm actually defining an inline function here. So in Python, if you have seen, we use lambda for defining an inline function. Over here, we just use function, function of x. I mean, x is just a parameter. It could be something else. And then you just leave a space and then write what your function actually does. And in R, the simple function is using the mean. The mean is going to be the mean of x because we chose a parameter to be x. And we also have another argument in here saying that na.rm equals true. So what is na.rm equals true? So basically, when you're taking the mean, what we're telling them is that remove all the na values. It is na.remove. So if you're finding the mean, if you have a missing value, it's going to show up an error. And the entire purpose of doing this is taking the mean of the non-empty values and putting it for the empty ones. So na.rm equals true actually helps us take the mean of all age numbers which does have a number to it, which does have an observation. So this is how, so basically I'll go back to this. So if the age shows NA, then you will replace it with the average of other variables. If not, the third argument comes in here, which is after the comma. This argument will be just dataset $age. So if it already has a value, which means it's not an NA, I just want to leave it as it is. So that's why I'm doing this. And I'm going to run this code. So if you see this green thing, it means I just ran the code. And if I check this data set again, you see this value in here. This one was NA, and it's got replaced by the mean of the other values now. Now let's do the same thing for salary. Now salary for the number 5 here, there's an NA. And let's do this. So what I'm going to do is just copy this code. And replace the age with salary. So yeah, make sure you have the same case. S is uppercase here, so you want to have S as uppercase here as well. So I replace this and we're done. We'll run this code and look back. Number 5. So this is the mean salary. We've done the mean imputation. So similarly, you can use median here. So I'm not doing this here because I really don't want to get deep into the data preprocessing side. So one other thing we can do is encode for categorical variables. So how R does it is because it uses this data type called factor. So if you look at the data set, the country, it's basically just 3 values: France, Spain, Germany, and purchases either yes or no. Technically, both of them are categorical variables. However, in this data set, they're not given as categorical variables because they're character types, not a factor. So if you want to tell R that these are categorical variables, you want to convert it to a factor. So the way of doing that is, and let's do it for country and purchase, both of them. So first of all, I'll be overwriting it again. This time I'm going to make this as categorical variables. Yeah, I'm going to override this. I'm going to choose country this time. And the function here is factor. And first thing is I want to override the same thing. So this variable is what I want to convert to a factor. And then there is labels. Let's take levels first. So this argument levels, it actually tells all the possibilities of all the categories that can come inside the country categorical variable. And the way you put this is actually using a vector. So a vector is similar to like a list, a 1D array. And the way of doing that in R is using C and then parentheses, and you can put the elements of the array inside this parentheses. So for country, it's just going to be, you have to put it in quotes if it's a character. So it's going to be the names that the data set can take. So it's France, Spain, and Germany. And you want to make sure that you use the exact same spelling because this is case sensitive. So Spain, Germany. So this is levels. So that tells you the range or the domain of the category. If you also need to have another argument in here called labels. And it also comes inside a vector, and it depends on what you really want to put in there. You could make these as numbers. So France becomes 1, Spain becomes 2, Germany becomes 3. But for this example, I'm going to put exactly the same thing as this. So my levels and labels are the same thing, and labels are just giving it a name. And actually, wherever you put in the labels, that appears inside the data frame. So if I run this, you see the change in here. Country before was a character, now it is a factor with 3 levels. Basically, it could have 3. It could be one of the 3: France, Spain, or Germany. And it's got these numbers right now, 1, 2, 3. It means 1 stands like the first row has 1, which is France. Second row has 2, which is Spain. Third row is Germany, like that. And if you just look at the data set again, you see it's not actually 1, 2, 3 as shown in here. It is actually France, Spain, and Germany, which is actually the names of the labels, not the levels. If I change this to 1, 2, 3, and if I run this, basically the levels also change to 1, 2, 3 over here. And if you look at the data set, country name becomes 1, 2, 3. So I prefer using this because it is more readable in that sense. So I will stick with this here. Similarly, we can do that for purchased, and it's going to be the same code with modifications. Purchased, this becomes purchased. The levels now are yes and no. And I'm going to make this yes and no as well. So this is also factors. So basically now R understand that these are categorical variables, and there can be like 2 categories here, 3 here, and these are the name of the categories. So yes, also one thing, since we did this as 1, 2, 3, and then changed it to France, Spain, Germany, this column actually became an NA. So the country column, if you see, is all NAs right now. And that is something you want to avoid. So basically, to re-get your whole thing, you have to like import your data set and do everything again. So basically, let's actually use this. This is when I click this, it's going to run all previous chunks. Over here, there's only 1. And now I'm going to run this entire chunk. So everything is run again. And now if you check the data frame, this should be fixed. And this is also a factor now, but looking from this, you cannot figure out whether it is a factor yet or not. So it is good to check the STR of the data frame every time you make modifications to the data frame. Also, one good advice is to create new data frames. Like it could be like a modification of the previous one and keep the original one intact, because you do not want to actually modify your original data, even if you're making changes to it. So we talked about categorical variables. Now the last thing I want to talk about in data preprocessing is to split the data set into training and testing data. So if you're familiar with machine learning or basic regression, or the way you do it in Python, it's basically you split it into training and testing, and you actually do your model for the training set, and then compare the results with the actual testing data just to make sure how good your model is. And that is often a good practice because it helps us actually it helps us in overcoming overfitting and underfitting. So this is something you might want to know before on. So actually there are many ways of splitting your data set into training and testing. And I will show you the most common method right now. And later in an example, I'll show you another way of doing it as well. So now let's, for this thing to work, the most common way of splitting, we actually need to import a package. So if you're familiar with Python, you say like import math, or from math import sqrt or something like that. So in this, how this works is you need to first install the package. So how to install a package, you write install the packages, and then inside this you put in quotes. It could be single or double quotes, it doesn't matter. And you put in the name of the package you want. So the one we are using here is called CA tools, and this T is uppercase. So you want to take care of that. And if you run this, it's going to install the package. I actually have this package installed, but I'm still reinstalling it just to show you how it works. And these are actually basically just warnings and things like that. So it is, if you're exporting this and you don't want this to be in your code, you can have a warning equals false. And I could just give this a name, data preprocessing. So that's actually making the code a little neat, more readable. Just it is like a one word documentation, docstring kind of thing. But yeah, it just tells the user like what is happening in here. So when it comes to install the packages, now you've installed the package. Now you do not have to install this package ever again unless you decide to remove it, or if there's a new update, you can just update it. So how would you call the package is using the library function. So library, and then over here you put in the name CA tools, name of the package, and this time you have to make sure that you don't put this in double quotes. If you put it, it might not work. And for installer packages, you need to put it in double quotes, and that's sometimes confusing for people. Sometimes they put quotes for the library, not for the installer packages. So if I run library CA tools, it's not going to show anything, but it worked, did not show me an error. But now when it comes to different packages, it might show you different things. For example, if I do a library of this very famous package called tidyverse, if I run this, it's going to show me all these things, like what, and actually because a lot of packages are part of tidyverse, and there's conflicts. Like sometimes what happens is two different packages have the same name functions, so it tells you what conflicts are there. And yeah, so basically tidyverse also you have to import it. So sometimes people get confused when to put codes and they do not like the installer packages. Sometimes it doesn't work sometimes they're using our script and then our MD and our notebook, and sometimes it just doesn't work. And even these things are very annoying in final reports. So how I usually go about this is when you want to install a package, you can go to this packages pane in here. Now over here you see a list of all packages you already have installed. You will have a couple of them by default. Now let's say I want to do the library of one of these functions. So this is AER, applied econometrics in R. I have this installed, and I'm going to click on this, and it basically does library of AER. And now sometimes you want to like kind of remove it, like kind of unlibrary. That's because you want to avoid a conflict or something like that. And there are other ways of avoiding conflict, which I'll go over soon. So you can just unclick this, and it gives you the code that you actually need to unlibrary it. There's no unlibrary function, but you have to use detach in codes, you have to specify that it's a package named AER, and then unload equals true. So that's the way of doing it. But if you want to install a new package, you can click on this install button. It's going to give you this thing. And there are ways of installing this package. Now it is the default R's repository called CRAN. That's where a lot of the packages we'll be using will be there. So you just type the name of a package here. Let's say tidy font. And it'll show you all the suggestions. If there's no package, if I just write something, it doesn't really show me anything because there's no package name like that. So I'll say tidyverse. I recommend installing tidyverse. You click on this and press install. I'm not installing this again because I already have it installed. The other way is by using package archive. So it tells you to actually take in a zip or a tar.gs file, which is basically someone's created a package, but it's not part of the R official repo. They have it, put it somewhere else, probably on GitHub or somewhere. You can download it and then install it that way as well. So this is how I usually install packages, and I do not include installer packages code in my code because you do not have to install it again if you have already installed it. All you have to do is call this library. So also the thing is, if you press like this and then use your code to work, but the thing is, every time you close R and you bring it back, you have to do it again and again. That's why I like to put the library part into the code. So this is the library we'll be using. Now, there's something I want to tell you, a function called set.seed. So what set.seed does is it kind of focuses, it gives you a number and it kind of randomizes in a specific order. So if I want to create like a random number, every time, if there's a function for that, every time it's going to give me a random number that's going to be different from what we had previously. So if you set a seed, it's going to randomize in the same order again and again. So sometimes you have functions in regression classification where it picks up things randomly, and every time you run your code, you get different answers, which is kind of weird. If you're working on a project, sometimes you say, oh, our accuracy is 0.8. Next time you run it, it becomes 0.6. So to avoid this randomness, we always set a seed, and you can put in a number in here. I usually go with 1, 2, 3, and that basically randomizes the code we are going to run after that. And the code here is split. Basically, we're creating a variable split, which uses the function sample dot split. You see, this is a package from the CA tools library. And basically, you write your y variable, your dependent variable. So as we said, we want purchase to be our dependent variable because that could depend on other factors. So I'm going to copy this here, and then I'll say split ratio equals 0.8. So basically, I'm telling that my dependent variable is from dataset. My dependent variable is purchased, and I want my split ratio. Basically, I want my training data to be like 80% of the data, and testing to be 20%. So that's what the split ratio tells us, 0.8. And to run this, it's going to create split. Now, let me run split in here. Basically, what split gives us is true, 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 false, false. For every observation we have only 10 observations here, it tells true. So basically, it tells us if it is true, then it is part of the training set. If it's false, it is part of the testing set. So this is how it works. So now you have to define your training set equals subset of. Now you're creating a subset of data set. And basically the condition for that is that your split value equals true. Now basically you have a condition in here, that's why you're using double equal to, similar to how Python does it. And the same thing for testing. Testing set equals subset, this becomes false. And if we run this training set, testing set, you see we have two other data frames in here. The training set has 8 observations, testing has two observations. That's like an 80-20 split. So this is how you'd split into testing and splitting. So this is one way of doing this. I'll show you another method in a future example. So now let's actually move on to the regression part of this. And the first thing I want to show you is how to import an inbuilt data set in R. So let's say I want to take this data set from called salaries, which is in the package car data. So the way of doing that is using data function, and you just write the name of the data set, salaries, and yeah, you have to make sure the case sensitivity is taken care of, and package equals car data. So this is the package in which this data set belongs, and I'm pressing this. Now what it does is it creates a value for salaries. It's not a data frame yet, so you want to convert it into a data frame. So there are many ways of doing this. One way is to use a function called force, and I will just put in salaries here, and when I run this, I get salaries as a data frame in here. So this is one way of doing it. There is other ways. So let me actually clear the environment. So if I clear the environment, all the variables and data sets I've defined, they all go away. So I have to rerun the code for whatever I want. And I usually rerun my clear my environment regularly just to make sure that the modifications I made actually do work. So what I'm going to do is do data again. Now it gives me a value. But now instead of using force, I'm going to use another method. This method uses this function called attach. And again, I'll put salaries in here. And it's converted to a data frame. Now, attach is a very common function used in R, and it is very useful. And it has its advantages. It also has its disadvantages, which I'll talk later in this video through an example. So for now, just want to tell you that if you're using attach, it is always good practice to detach. The same thing, and this doesn't really affect our data frame, but it is good practice, and I'll explain you in detail when we come to an example where we are actually using this and analyzing its advantages and disadvantages. So this is one way of doing this. Now, if you want, let's actually look at STR of it. So we have categorical variables, which is factored, and we have numbers. Then we have like 397 rows and 6 columns in here. And if you want, you can view this. And if you see rank, basically it says 3 levels. We can see it's professor, assistant professor, and associate professor. And there's sex variable, which takes male and female, and the others are just numbers. Discipline is also a factor. It could, right now it's B, A, and it sends to levels A and B, so that's it. And the rest of them are numbers. There's a variable called years since PhD. There's years.service and salary. If you don't know what these mean, we can always check its documentation. So in our, if it is a built-in data set, most of the time is going to have a documentation. Sometimes it does not. So let's actually look at how to get to the documentation. So if it is a data set, you can just press question mark and write salaries and just run that code. And it's going to show this in the help over here. It tells you the description. It's like a 28 to 29 9-month academic salary for professors in a college in the US, and data was collected by the college administration and stuff like that. is usage, the format, the variables, what each variable means. Rank is a factor. Discipline, years since PhD is years since a person, the professor has gotten their PhD. Year service, that's the work experience, I believe. And yeah, there's a reference to the original article from where the data was collected. So this documentation is great. Also, if you have a function which you forgot how to use it, let's say Shapiro the test. This is actually the function for doing Shapiro work test. It checks if a given vector is normal, is distributed normally or not. So if you are confused about a function or a data phase, what a data set, what it means, you can always go to its documentation, check its value source. Sometimes there's examples given, sometimes it's so detailed that it is the best thing you can have. So yeah, this is how to check the documentation. So now we have an idea what salaries actually means. So now actually let's run a simple regression. And it's going to be a linear regression. So how we call it is like we assign it to variables, a regression object called model. So you can name it whatever you want. I go with models and fit or something like that. So the function to use here is called LM, stands for linear model. And in this, basically what you want is you want your Y, and then you want tilde X, which means this is your dependent variable and depends on X, comma, data equals the name of your data set. Over here is going to be salaries. Now let's see, what do you want to predict? What is a dependent variable? What is an independent variable? So if you look at these variables, it kind of makes sense to check if the salary of a professor depends on his or her rank, or the number of years since they've got their PhD, or number of years they've been serving, or even their gender. So we want our Y variable to be salary. But yeah, so the thing with salary here is, since you're using data equals salaries, it does understand that we're taking this column from this data set. So you do not have to write salaries, $ salary in this case, because you're mentioning your data set. And X, it could be any one of these, it could be more than one of these. Let's say years since PhD as our independent variable. And if I'm running this, you see I have a model in here. If you're going to try to read this, you're probably not going to understand. If you click on this, also it gives you a lot of information. But if you want like proper information about your model, the best way of doing it is summary. And inside the summary function, you put model, and it gives you this whole list of information. So first of all, it tells you what your equation was, and then it tells you about your residuals, the minimum, maximum, the median, the first and third quartile. It tells you the coefficients. Now the intercept, it tells you, basically if you see, it's going to be like a linear model. So it's going to be like y equals mx plus b, that kind of equation. And this is the intercept, and it tells you the standard error, t values. If you know statistics, then you're probably familiar with t values and p values. And the p value this time is very small. It's less than 2 times 10 to the power negative 16. And these stars actually tell you about how significant it is. So if you have your alpha value, which is the probability of type 1 error, also known as level of confidence. So if it is, mostly we all choose 0.05 as our alpha value, and any p-value less than that means you reject the null hypothesis, and if it is more than that, you fail to reject it. So over here it's very small, so we fail to reject it. And these 3 stars means that your p-value is actually smaller than 0.001. So even if you had a alpha value of 0.001, you would still fail to, you still reject this null hypothesis. And if you know about regression, your null hypothesis is that your beta one, that is the value here, which is the coefficient of your independent variable, is 0. And if the coefficient of your independent variable is 0, it means your equation is just like the dependent variable is a constant, which means that it does not depend on the other variables. So if you reject the null hypothesis, it means that there is significant association between these two variables. So this one also has high p-value, 3 stars, very low p-value, sorry, we reject it. And basically, if you had 2 stars, it means you can reject it at an alpha of 0.01, but not at 0.001, which means the p-value would be between these two numbers. So that this is just like a navigation tool. So usually we are interested in more than 1 or more than 1 stars because they're like less than 0.05. Sometimes when there's a dot, it means the p-value is more than 0.05 but less than 0.1, which in some cases we might want to consider that. And if it's empty, basically there's nothing after the p-value, it means that variable is not significant. And also there's a lot of other information. We have our residual standard errors, the degrees of freedom, our multiple R-squared and our adjusted R-squared. Now, if you're not familiar, multiple R-squared is basically explaining the variation in your model, like how much your model explains the variance. And basically we want it to be, it's between 0 and 1, and we want it to be as high as possible. So that means more the model explains the variation in the data. So this one is pretty small over here, but still this is significant. So there is relation, but the model is not that great. And there could be several reasons for that. It could be that we're missing another important variable, or it could be many things. It could be like dual causality and something like that. So, and adjust basically multiple R-squared, the formula for that is 1 minus the residual sum of squares divided by the total sum of squares. If you don't know, it's probably okay at this point. The adjusted R-squared, we will talk about that when we have more than 1 independent variables, because we do not actually need this for a simple regression with just 1 independent variable. It has your F statistic as well. It has the degrees of freedom, the overall p-value. So overall p-value in this case is going to be the same as this one because there's only 1 independent variable. But when there is more independent variables, it's going to change. So this is the basics about this. Now I want to show you another way. So let's say if I just put in model over here, I'll put it in here. It just tells me the coefficients, which is like an easier way if you just want the coefficients and nothing else. But yeah, of course you need to check which variables are actually important, significant based on your alpha value, things like that. You might not want to use this a lot. There's another thing I want to show you. So let's actually, there's an package in R called Stargazer. So you can go to packages, install, type in Stargazer, and I actually have it installed, so I'm not doing it right now. So I'll just do library Stargazer, and from this Stargazer library, I'm gonna use the Stargazer function. It's the same name for the function within the library. So also, yeah, one thing I wanted to tell you, like if you have a conflict and you want to make sure that a specific function is taken from a specific library. So basically what you do is you write the name of the library in here, put in like 2 semicolons, and then use the name of the function, which means this is like library name for 2 columns, and then the function name over here, they are the same, but it may not be the same. And it is actually good practice to write like this because it makes your code more readable. And if you put in this thing, is going to show up your summary in a more neat way. And if you're creating a report, I would go doing it this way instead of using summary of model. And basically how I do it is I just put the model in here. And the second argument I have is type equals text. So you could make this to HTML. You can make it to text. but this is the most straightforward way of doing it right now. And if you see, it's going to give you this thing. It's going to tell you your coefficients, and it's going to tell you if it is significant or not. It's like both of them at the same time. And then it tells you how many observations is there R squared, your F statistic, or F studios standard error, and it's this thing. So if you've kind of seen research papers where they have a summary table of their regression model, this is a similar format on how they put it. So this is a really important way of doing this. Also, now let's actually move on to multivariable regression. Let's add another independent variable. So multiple and here basically I'm just going to create another model which is going to be like same as this, but I'm going to rename this to model one in here. I'm going to add a second independent variable, which is just adding a plus and then writing another variable in there. Let's say ears dot service, and I'm going to run this. It's going to be stored in model one, and I do summary of model one, and you see you have two variables now. Both of them have their own coefficients. And if you see ears as service, it has only one star, which means it is significant at 0.05. But it's less significant than ears since PSD because its p-value is even smaller. And our multiple R square is now 0.1883. What we had before was, let me just run this again, summary model. What we had before was 0.1758. And this time it increased to 0.883883. But multiple R square is actually not as accurate for more than one multiple variable, more than one independent variables. And this is because the more variables you add in, your residual sum of squares is going to decrease. No, it's going to increase with respect to your total sum of squares, which means multiple R squared is almost all the time going to increase, even though you add in a variable that actually does not affect your dependent variable, which is actually contradictory. So for that case, we define another thing called the adjusted R square, which is basically the same as multiple R square, but it now has a penalization factor. So the more variables you add in, depending on how much it affects the dependent variable, it penalizes your R square, which means it's usually less than your multiple R square. And this time it's almost the same. So this is pretty good model, at least the way it is right now. Probably not the best model because these values are really small. We want it to be like more closer to 1 than 0. So this is how multiple variables work. Now if you imagine, when talking about categorical variables, like let's say categorical. Let's say in my model, I'll just create a second model. I had a model 1 here and a model 2, and I'll just add sex. So sex is actually a factor. It takes variables like male, female, and imagine if it's there in this model. It doesn't actually make sense to have a coefficient multiplied by male or female and have it in an equation. It doesn't really make sense. It's like multiplying and adding with a number with like strings and things like that. So what if I want to add a categorical variable in the model? How does that work? So the thing is, R actually takes care of it themselves. So basically what it does is it encodes the variables using binaries, zeros, ones. I mean, if there are more than 2 categories, it could be 0, 0, 0, 1, 1, 0, 1, 1. So if you want to see how R actually categorizes things, we can use contrast. Contrast function and you put in this time you have to use the data frame dollar the name, and if you run this, it's going to tell you that hey, in the model, what it's going to do is it's going to take female as 0, it's going to take male as 1, and then actually do the model. So R takes care of that pretty good. So let's actually run this model with sex added to this variable. And if you see the summary, if you notice, now you have a variable called sex male, which is not what we had before. We had sex, and which could take male or female. But since if you go back to contrast, the thing is female takes as 0. So if there's a coefficient that's multiplied with 0, it's not going to be there in your regression model because it just sums up to be 0. So this method is actually not very good because the effect of the gender being female on salaries actually becomes a part of your intercept now. So basically the intercept, the constant is going to increase because of that. And it's creating a variable called sex male, which it actually only talks about the gender being female. And the dependency of it being female is a part of this now. And you don't really know how much of this is actually about the sex female. So when it comes to categorical variables, if you want these statistics, then this is a good way of doing it. But if you do not, if you want to separate your sex into sex male and sex female, which is inside the intercept, there is a way of getting around that. And that uses actually a new package. It's called car. So I already have it installed. If you don't, you can go back to packages, install, and do it. So I'm just going to call library of car. Okay, I have to run this. And from that package, I'm going to basically just call this function called ANOVA with a capital A. If you're done statistics, you might have heard about the ANOVA table. You usually draw in regression. I've done a lot of those by hand. And ANOVA basically stands for analysis of variance. So ANOVA, and I just put in model 2 in here, and it's gonna give me an ANOVA table. It says type 2 tests. And basically now you have sex as a variable on its own, and it tells you which variables are significant. If you compare this with the summary model 2 here, so if you see sex male had a p-value of 0.07 and it had like a dot there. If you check here, it is also 0.07, but it's different. It was 0.701 there, it was 0.7008, which is almost the same, but it may not be the same all the time. So technically, if you do summary model, it's going to tell you if sex is actually dependent or not, just from this. You do not need to do this ANOVA, but it really depends on what you want to find out from this regression model. It depends on what you want to conclude, that you might use different functions. So this is the way about going about for categorical variables. Now, I also wanted to show you how to do, like, let's say your data frame has like 50 columns, and one of your columns is salary, which is your dependent variable, and you want to regress that on every other variables, like all the other 49 variables are independent variables. It is very difficult to type each one of them, adding a plus and then typing the next one. So R has a shortcut for that. Let's actually call it model 3. I'll copy this from here. And the only difference is that now you have salary tilde, and then you remove these and just put a dot in front of that. Dot means like every other variable other than salary from this data frame. So this is going to regress it on all variables. And if I do summary, it's going to give me this. Now, discipline also was discipline A, discipline B, and it was categorical. So this is how the summary function works. Even for rank, rank had 3 ones. It has professor, associate professor, and assistant professor. So let's see the contrasts for rank actually. Contrast for salaries or rank, and it's basically doing 0, 0 for assistant. So that's going to be a part of your intercept now. Now associate is going to be 1, 0 for professor. It's 0, 1. That's why these two are there over here. So this is a good way, a short, succinct way of doing this using the dot. So that's what I wanted to show you here. So now let's actually move on from this, and let me show you how to do transformations. So, sometimes you want to create a model, regression model, where you want to regress a dependent variable on like the log of another variable or like the square root of another variable. And it really depends on your domain. Like if it is like, if you're working in healthcare, you probably already know, like your domain expert already told you that this variable depends on the square of this variable. So you might want to create a regression model for that. For that, you'll need to do a transformation. So I'm going to copy this transformations. And let's also talk about interaction terms. I'll come to that. So I'm going to create a model for, now I want to do salary versus the square of years since PhD. So what I'm going to do first is years PhD square. So if I do this, like squaring, this is how it works. If I want to do like 5 square, it'll give me 25. But if I do it this way, I'm going to change this to 4. It's actually going to show as an error. Oh, it's actually not showing as an error because this is only one variable. If you have multiple variables, this way is not going to work all the time. And also there is logically an error in here when it comes to real practice, and I'll talk about that. So at first you get this, but in R, if you want to do the square of a variable, you always, if you don't want to avoid logical errors, you always have to do it the original variable plus the square of it. And that's when you get like the true values. And if you want to do a cube, you have to have the original variable squared, and then the cube. And that is how it actually works. So now, so the thing is, if you did a square and a cube, this actually did not give us the square and cube in this. And that's why I was saying that there might be an error in this. And the way R works is it does not really understand this as square in the first place. If it was like just this variable, it would have understood it. So what you need to do is you need to enclose not this one, but the square and the cube into a function called I. So basically it's just I, and then in parentheses, you add this. So it's telling that we're doing a transformation. And if you run this, now if you see, you have the variable squared and it's cubed. So this is how you actually do it. And you could also do it directly cube like this, but you're going to get a different answer. Which, if you see over there, we did not have 3 stars before. If I just go back to this one, you see it was actually empty here. So there is logical differences between 2 different methods, and this is the way of doing it. If you're doing a polynomial, you have to have all its degrees lesser than that included in the model. And yeah, if you're doing a square or something, it has to be inside I of that. So that's model 4. And yeah, if you want to do log, then let's remove this for now. If you want to do log, you again put this into an I, and inside I you'll put the log because it's still a transformation and it's years since PhD. And if you run this, it is going to give you the log of that. And this is pretty neat. And if you see, its multiple R squared is 0.2459. If we initially, when we did it, it was like 0.17, which means the log transformation is actually better in this case. So this is how you go about doing transformations. Now let's talk about interaction terms, like I'll say model 5. And let's say your domain expert told you that your dependent variable actually depends on the product of two independent variables, not both of them individually. So how would you do that? So let's say it's year since PhD, and it is year's service. This is just going to give us two different variables, but it's not going to tell us like both of them combined affect salary. So how you do it is you put a colon instead of a plus sign in here, and when you run this, probably going to have summary model 5, and you run this, you see this is year since PhD colon years.service, which means there's only one term, which is a multiplication of years since PhD and years of service. And if you see this is 0.05, this is a very bad multiple R square, which means the product of these both do not affect salary that much. So this would actually be a better model. So, just for illustration purpose, I'm going to leave it over here like this. So that's about these transformations. Now, the thing with transformations is you never really know which transformations to use. And it's not like you can try every transformation in this world before doing your model. So also these transformations, it just does not work with independent variables, but it works on dependent variables as well. Let's say I made this as I of log of salary. And I'll run this, and it's going to give me log of salary regressed on log of year since PhD. And this is 0.27, which is greater than 0.25. So this is better than just the log of year since PhD. And similarly, you can do salary. Okay, you can do the log over here as well. It's not going to make a big difference. Also, transformations. Okay, so there is another transformation I want to talk about called the Box-Cox transformations. So with the Box-Cox transformation is just a transformation for the dependent variable. Now, basically, it finds a value called lambda, and this lambda value is going to be the power of your dependent variable. So sometimes you can do salary cubed, but let's say salary to the power of 5 was better than salary cubed in here. So how do you find the optimal number? And that's a method called the Box-Cox transformation. So I would basically, I'm just going to create a variable called sal equals salaries. And I'm going to put this brackets. Now, what this brackets is, I'm basically creating a new data frame called sal, which actually we do not need this. We can directly do it from the salaries one, or maybe just to check for normality. Let's create the sal. So if I put a number, I say 1, not 1, 2, but if I put it on vectors, 1, 2, and then another vector 1, 2. Basically what this does is it takes rows 1 and 2 and columns 1 and 2. The first argument is for the rows, second column is for the columns. So I want all the rows. I do not want to remove any observations, and I'm basically gonna pick up columns 3, 4, and 6. And why? Because salaries not salaries. Salaries columns 3, 4, and 5, 3, 4, and 6. These are the only ones that are integer values. And the only reason I'm picking out only the integer values is because I want to run a normality test. So I'm going to run sal, and then it'll give me a data frame called cell, which has only these three values. Now, let's run normality tests. Shapiro, I showed this to you before, Shapiro.test, and it's going to be cell dollar. You have to do one variable at a time. So you could have directly used salaries, but the reason I prefer bringing all integers to a different data frame is because I could just use a for loop to iterate over every column and make the code like more easier and faster. So, but I'm going to just show you one variable right now. So sal underscore year since PhD. And if you see, we get this results. So when it comes to Shapiro test, the null hypothesis for it is that the data is normally distributed. So if you have a p-value that is less than 0.05, it means it is normally distributed. But this is how you do it for year since PhD. But for a box-Cox transformation, the assumption is that your dependent variable, which is salary in our case, is going to be normal. So I'm going to do the Shapiro test for salary. And if you see, this is also very small, which means it is normal. So no, actually the null hypothesis means it is normal. So I'm really sorry, we're rejecting the null hypothesis. That means it is not normal. So the box-Cox transformation does not apply for this case, but I'm still going to show you how to do the box-Cox transformation in case we have a dependent variable that is normally distributed. So for that, it requires another package called mass, all caps. And from the mass package, we'll use it later, but let's actually bring back our model one from here. To take as an example. So I'm going to run this and I'm going to rerun this model one and summary. And what I'm going to basically do is create a box-Cox object. I'll name it box-Cox BC. And this uses box-Cox. If you see, this is from the mass package we just used. So I'll just put a mass this over here. And from this, I'm going to just put in model one. And you do the box-Cox here and you do lam equals, let's call it best.lam. This is going to be the best lambda value. As I said, lambda is going to be the power of our dependent variable. So if you do best.lam equals to, now we'll do BC, this is the box-Cox object we have, $sign X, which is it's going to be like a matrix of our independent variables because there are more than one. And then I'll do which is a function that actually tells us, actually gives us values from these matrix for a given condition is inside which. So I'll say BC or Y, that is the dependent variable, equals max of underscore Y. So this is just how, this is like the theory behind box-Cox, which I haven't explained it to you. So if you don't understand it, it's fine. Know of this code and I'll just print on best.lam. So let's actually run BC best.lam. So if I have a BC, it'll actually give you a plot. So this plot gives you the different values lambda can have, and the maximum value of lambda is here. So this is where you have a really good model. So, and basically best.lam will calculate this lambda value because you can't really see it from the graph here. And if I do best.lam, it's going to give me this number. It's minus 0.222. And if I want to create a new model, I will say let's create model 6, which is going to be similar to model 1. But this time, salary is going to have this thing, a transformation, and it's going to be salary to the power best.lam. And if I do this, I can just run this here. I actually went this to model 6. No, yeah, model 6. And if you see, this is our function, and our multiple r squared equates to 0.19, which means this actually does work, but it's not a big difference anyways. So you might want to use it if you actually need it. So of course your domain expert would be the one who will tell you when to use this, when not to use this. It really depends on your case study. So this is about transformations. Now let's actually do some regression using the training and testing data, because in practice we're going to do that all the time. We're not just going to use the original data set in here. We're going to train the model with the training set and then predict our expected versus observed values using the testing set. So let's actually use the same example here. Let's say predictions using train test data. And basically, as we don't have to do the library of CHOs again because we have already done that before. So we just, okay, let me just go back to the preprocessing and copy this much. The code is a bit more efficient. And this time our data set is called salaries. And our dependent variable is salary. And I think that is about it. So I'll run this. So we see if we use the same name split training set and testing set, basically it's just going to overwrite the ones we had before. So these are the latest ones. You see, testing has 80 observations, training has 317, which is approximately 80-20 split. So let's create model 7. Now I'll do model 7 equals LM, and it's going to be salary. So that dot, I'm going to use all the variables in here, and data equals salaries. And no, actually, before we had salaries, but this time we're going to use training set. So basically, you're creating the model using the training set, and you want to define the predictions. So I'll use this variable called ypred. We'll just use the variable called predict. So predict is from the stats package, which is by default already loaded, so you don't have to do stats, library stats, or even install it because it's there by default. And you will just have a model 7 in here and use test underscore set, testing underscore set. So basically you're predicting using a model the values for the testing set. And ypred, so this is just to see how it will look like. So let's run the model ypred. Now ypred, if you see, it gives you numbers for each observation, and these numbers are basically the salary predictions for the testing set. So basically what it does is from the testing set, it takes all the variables other than salary, and using that as the input into the model, it predicts the salary. Now, these are the predictions we have. Now we want to actually compare it with the actual ones. So what I'll do is I'll do data.frame. In data.frame, I'll have ypred, comma, testing set salary. Basically, it's going to give me a table where you have ypred in here and you have the actual salary. So this is the predictions and this is the observed values. So you see the numbers are quite off because the model is in that grade. So it's still not that bad, but it's pretty good. So this is how you would go about doing this in practice. So now I want to go to what's called variable selection. So let me create a new code chunk. This is too big. I'm going to make two here because it's a second level heading. And that's because it's still a part of regression, but it's a special topic. So let's say the idea behind variable selection is that let's say we have many independent variables, and some of them do not actually affect your dependent variables. So we don't want it to be a part of our model. So how do we select the ones which are actually significant to our model? So let's actually use another data set for this example. We're actually going to do two types of variable selections. So let's use, okay, so I'm going to do data Swiss, because this data, the Swiss is now part of the values. You don't have to use the package because it's there in R by default as part of default package. So now let's actually do attach Swiss. As I told you before, attach has its advantages and disadvantages, and you might always want to detach it. So once I do attach, it becomes a data frame, so it's usable. Now, the thing with attach is, let's go to Swiss and let's find a variable. Okay, okay, let's just try out creating. Okay, before we create a model, I'll just say, let's find a column, let's say agriculture. If I press agriculture, it's going to give me the values of agriculture. Now, if you notice, we didn't have to mention Swiss $agriculture, which is supposed to give you that. How does R know that this agriculture is in the Swiss data set? Now, if, like, for example, if I do salaries underscore salary, but just remove this part, just do salary. If I run this, it's going to give me an error. It's not found. But for agriculture, it worked. And that's because we attached it. So the thing with attach is it makes the data frame kind of global, which means if you're searching for a variable, like a column in this case, it's going to go to the global data frame and see, oh, hey, agriculture is actually a column in this global data frame. So this is what they actually want. So if you have a really big name for your data frame, it is good to attach it. The problem with attach is if you keep attaching again and again. So let me actually run attach again. It's giving me the following objects are masked from sys position 3. If I do attach again, it's going to show me twice. And this is actually going to cause problems because there are multiple global Swiss data frames going to be created now. So for that, you need to detach. And for every time you attach, you need to detach. So I just detached once. I'm doing it again. I'm doing it again until I get an error, which means now Swiss is no longer a global thing. And I'm going to attach it, do all my work, and then detach. And also another reason you want to detach is sometimes there are several data frames that have a same column. Let's say there was another data frame which had agriculture as its column. And I would attach both of them and I would do agriculture. It would still give me an error because it doesn't know which of the two global data frames agriculture came from. So it is always good practice to have attach and detach. So let's actually go around with variable selection. The first method we're going to learn is called, let's make some space, called best subset regression. So that subset regression, basically what it does, it tries to see how many independent variables is optimal for our case, and for every optimal one, it sees which variables are the most important, and it includes that in the model. So this requires library of leaps, this package for leaps, and from that we'll create an object called models, because it's going to calculate a lot of models at once, and leaps reg subsets. This is the function we want, and basically what you do inside that is similar to the LM part. So if you go to Swiss, let's see what we have. Let's say our dependent variable is fertility, and everything else is our independent variables. So we have fertility dot, and I'm going to use data equals Swiss, and since this is reg subset, is going to have another variable called n max. It's an argument. Now this is supposed to have a number. I'm going to have it 5 in this case, and why 5? Because I go to Swiss. So what this number does is it checks how many independent variables is optimal. So we have 5 independent variables, and you want to check out of all 5. I mean, let's say if you have 50, you will have it at 50. You can have it less than that because you want the model with less variables, not all of them. But this is like small number of columns, so we'll just do it for all of them. And then we'll do summary of models. So I think I haven't run the library yet. So models, summary. The thing with summary is it gives a lot of information. There's a lot of first in, first out, which is not so important. What we need is this bottom half. So what it says is that if you have a model with one independent variable, one independent variable, it is better to have education as that one independent variable because it is more significant. If you want to have 2 variables, education and Catholic are the ones that explain your fertility the most. If it's 3, then it's going to be education, Catholic, and infant mortality. So basically, in that sense, I would just say I have it typed it here. So the best 1 variable model will be fertility to the education. 2 variable will be education, Catholic. 3 variable infant mortality comes up, and then over here agriculture comes up. Over here examination comes up. Then it kind of makes sense because examination doesn't really affect the person's fertility. So this is how this works, but we still haven't found our answer yet. Like we found which number of variables will give you which variables, but which of these 5 are going to be optimal, we don't know yet. So for that, we have another part of this part. It's still part of that subset regression. We'll create the summary as a variable because we'll need that. I will say models.summary equals this. We'll store it in a variable. And now so basically there are different metrics to do that. Like until now we have been talking about R-square and adjusted R-square, but now there are different metrics to do this. So let me actually show you this one. So model performance matrix, there are a lot of them. So R-square, we talked about that. Then there is root mean square error. So basically what it does, it's first of all, you do all the every observed minus predicted value, you square it, you do the mean, and then take the square root. And that's one metric you can use. There's standard residual standard error, RSE. There is mean absolute error, that's like the mean of the absolute value of the observed minus predictions. These are all ways of doing model performance, for checking if a model is good or not. But there are other sets of ones as well. There is adjusted R-square, what we talked about, and it's actually better than R-square because it penalizes, especially when you have more than 1 independent variables. And there are other ones. There's AIC value called Akaike's information criteria. It's developed by a Japanese statistician, which also has a penalization factor included in it. And there is AICC, which is a version of AIC, but for small samples. There is BIC, called the Bayesian Information Criteria. And it is also a variant of AIC, but it has a stronger penalty, which means it penalizes even more, which is why the BIC value, BIC value, is the most commonly used metric for best variable variable selection and best subset regression. And there is MALCP. It is also a variant of AIC. So we'll mostly be using BIC value, and I'll show you how to find the BIC value for all these models. So yeah, here we are. We'll first make a data frame because we want it in a table format for multiple metrics. We'll do adjusted R-square, we'll do CP, and we'll do BIC, all three of them. So we'll have adj dot r2. It's just a variable name. You can name it something else, and you'll say which dot max. So it's similar to the which function I talked about before, but it finds the max over here. And from the models.summary, so we want daughter adj r squared. So it'll take of all these 5 models, which one has the highest adjusted r squared. That's what it'll find out. And it's going to be similar in the next line. This becomes CP, and this becomes CP, and this becomes BIC, and this becomes BIC, and we'll just run this, and we get this table. They say the 5th model according to the adjusted R-square metric is the best. According to CP and BC, they say it's the first one. So that is, and we usually go with the BIC value. That is why I would go with this first one here. So this is how you exclude variables you do not need, that do not actually help you in getting a good model. So this is one way of doing variable selection. Now there is another way called stepwise variable selection, for which I will use the same data here. So stepwise variable selection. So how this works is we'll go back to this, and let's see. There are 3 types of variable selection. There's forward, backward, and there's both. So what happens with forward stepwise selection is, let's say you have 5 variables, independent variables, and you have a null model. You can have maximum 5 of them in there because there are only 5 independent variables. And what it does is it does a regression of y on all of these separately, like with one variable only. So it's like y to the x1, y to the x2, y to the x3. It does all of them and checks which one has the highest, most significant. And of course, it can use any metric it wants. It could be r squared, it could be AIC, whatever it is. And it actually finds the variable with the most significant explanation of the model. And then after you have fixed your first variable, it tries to put in the second one. And it finds, it's like an iterative and recursive way. It tries to find the best models to put in. This is forward. There is also a backward method, which works in a very similar way. So this one is backward stepwise selection, which basically starts at the end. It does all variables first, finds the least significant variable and removes it, and then finds the least significant one and then removes it again. And that's how this method actually works. So this is the backward stepwise selection method. So let's see how to do it in R. So for this, we will use the mask package. We already did the library of that, so we can do it again. So let me name this as fit as a new model, and LM fertility. So I'm using LM in here because it's different from like subsets, but it's technically the same model. And then I'll create a variable called step, which from the mask package calls STAT AIC, and basically just putting the model in here, and we'll specify the direction equals, we can make it as forward or backward or both. So what both does is it actually does forward and backward both, and then compares the values in this. And so basically it's a recursive process. So both is something what people usually prefer because it gives efficiency, but it takes more time than doing forward and backward. And for us, it's like a very small data set, so it doesn't really matter. And there's also a variable called trace equals, we can make it as true. So what if we do true, what it's going to do is for every iteration, like everything is going to show us how it computes. So I'm going to put step here again, but I'll do this for step, and then I'll print out step. So in this, it was very easy. It was just one thing. If I do backward, it's going to show you a lot of information because every time it iterates in the recursion, it's going to show you. So I usually keep it as false, trace equals false, because all I care is about the final answer, not the intermediate steps in here, unless you want to show that. So it gives you the model with the intercepts already, and according to this, there are like 4 variables. In previous one, we had only 1 variable. So there's different methods, depends on your case study, what you want to do. Your domain expert will tell you when to use which method. So this is about variable selection. Now I want to move even further from that into what's called penalized regression. So I don't know if you've heard of them. Penalized regression basically is penalizing. So basically now, until now, what we're doing is BIC and just stars, where they penalize the model metric, not actually the model. So this time we want to penalize the model as much as we can. That has different methods of doing it. We are covering 3 of them, which are the 3 most common ones. They're called ridge regression, lasso regression, and elastic net. So let's import another data, and let's do it from our local directory this time. So I have my directory in here, and it's going to be in this Ames housing data set. So actually R has it inbuilt, but I'm still going to read that from this file, because this file I got it from Kaggle. And thing with Kaggle is because they made it neat. Like if you take the original data set from the built-in R, it's going to be difficult to do the data pre-processing before we come up to the actual implementation. So just to make things faster, I'm actually just gonna copy this from my directory, read it from there. Now Ames. Now we can have a look at the data. It has many columns. You can see it's like 20 columns and 1430 rows. It is a lot, but not that much. That's really good with that. So there's a lot of variables, and we don't know its documentation as of now. So we'll just go ahead with str of Ames to understand what we have. So most of them are integers. There is 1 character in here called central error. It is mostly numbers. So also, if you want to check if there's any missing data in your data, there's a function called NA. You just put in the data frame Ames, and you run that. It will say false, which means there's no missing value in any row or column. And if there was, it will give you yeah, it will give you true if there's NA. And we'll also look at how to remove missing values later on in an example. So this is one way to check if there's missing data. And if we took the original data set, which was from the built-in R, we would have missing data. So it's good we're importing it from here. So now let's actually split this data into testing and training. So as I told you, there is other ways of doing it, and I'm going to show another way of doing this, but that also requires set.seed. And this actually uses a library. Let's import that. I already have it installed. If you don't have it, you'll have to install it first. It's called Caret or Caret. I don't know how to pronounce it actually, so let's go with it. And I like this one. It's almost the same number of lines. It works exactly the same. I think, okay, it shouldn't be a problem. So, but I like this method better than the previous one. It almost does the same thing, but this is how I learned it when I learned it for the first time. So similar to the split function we had before, we will make it as training samples. So just a variable. And what I'm going to do is from this package, I'm going to have a function called create data partition. Create a partition for the data. Again, you have to give your y variable. So we still don't know what this means, but let's say y variable is sales price. That makes sense. You won't predict a price. And let's actually do it 75% on testing training and 25% training testing. So let's do this equals false. This is the parameter in this. It's required. And then what you have is train data. I'm just getting different names. So we will just have this here. And basically I'm just going to put in training samples and then a comma, because we are actually taking the rows of the training and sample. We're not splitting it by columns. That's why I'm going to have this comma empty, because all the columns will be there. And similar, I'll do test.data, and this I'm going to make it minus training.samples, and I'm going to do the trick. So tendency, this, and we have train and test.data and train.data, 363 and 1097, fairly 0.75 ratio. So yeah, so let's go about doing the thing. So how ridge lasso and elastic net works is because it has function lambda. Show you here. So basically what it does is, now you have your cost function. This is basically your regression line, and you know your line is going to be like y equals mx plus b, that kind of format. And basically this is, and multiple variables have like mi, xij minus b, different variables. That's why you're summing over all of them. Now what it has is an extra term, that is lambda times m squared. M is basically a coefficient of one of the independent variables, but you're summing over all of them and summing over squared of all of them actually. So this is basically called L2 norm regularization. So it is basically a kind of penalization factor, and which is why the name for this technique is called penalized regression. So this is how ridge regression works. It has this penalization factor in here, and this, but for doing this, we have to try out different values for lambda. So what we do initially is we create like a whole set of values lambda can take. So I'm just going to do lambda equals 10 to the power. Now it's going to be a sequence, which will tell you like it ranges from one value to one value. So it's going to be -3, 3. It really depends on what you want to take. It's not really it doesn't really make a lot of difference on how you define lambda. Just not important at this point in time. So I'll create lambda, and then I'll do rich regression. So the thing with rich regression is it trains a model. It's similar to an ML, but it's a different model. You will need to do the set.seed, and I'll call this model ridge. And I'm going to use a function called train. This is from the caret package. This is exactly why we had the caret package loaded. So train. And you basically just going to have your sales price to the dot data equals training set. Let's train the data here. And you have to give a method called glmnet. This is how R works, this thing. And actually, let's put these in different lines because there's a lot of arguments we need here. Then we have what's called TR control. And basically, you have train control. This is a function. If you always want to check what these means, I mean, it's not really important at this point in time what these mean, but this is how the regression works in here. So this is from the caret package as well. So yeah, in this, what you're going to put is STV, because this uses penalized regression uses method of cross validation. And to be specific, it's going to have a number. I'll put it as 10. It's going to be 10-fold cross validation. If you don't know what it means, it's not really important at this point in time. And then there's tune grid. This is because we are using several values for lambda, not just one. So we're just going to make expand. This is a function, expand the grid. And it's going to be alpha equals 0 and lambda. That's basically this lambda we defined. So I think I haven't run lambda here. And basically this is going to give us our ridge model. So if you just do ridge here, I don't think this is going to catch. So if you run this, it's going to give you a whole list of values. It's really bad to see that, especially in a report. So you'll do ridge $sign. Best tune will give you the best lambda value at which you get to do final model in here. And there's still a lot of information. Sometimes it doesn't give it in a readable format. And sometimes it gives like so much information that you might want to stop the console and clear out the console just to make it clean. This is why we usually do not print ridge models. We just create objects and then we find metrics, we print the metrics from it. And I'll show you how to do that. I'll make it into like small table for all ridge, lasso, and elastic net at the end. So let's do lasso. So LASSO. So how lasso works is basically it's similar to it, but instead of taking this penalization factor as the square of coefficients, it takes the absolute value. That's the only difference. It has different penalization factor, and this is called L1 regularization. So that's how it works. And the code is going to be pretty much the same. Again, you're going to train a model, so you need the seed 1, 2, 3. And I always try to keep the numbers consistent. You have different numbers. Like I could say 1, 2, 3 here. Over here, I could say 3 to 1. And it really depends on the model you're training right after that. So you're going to get the same numbers every time you do it because you're going to run the same code with the same seed every time. But I always try to keep my seed number consistent across code, although it's not necessary. So it's kind of to make it neat. So for lasso, it is almost the same thing, But this time you're going to have alpha equals 1. So over here, alpha equals 0 actually meant that you want to do a ridge regression. Now alpha equals 1 means you want to do lasso regression. That's the only difference. Everything else remains the same. And I'm going to do set.seed. And I realize I have to change the name. And we have this. Also, again, you do not want to print a lot of stuff here. So let's move on with ElasticNet. This is what people use most of the time, but it's not necessarily the most optimal one every time. So if you go to ElasticNet, it's basically both L1 and L2 regularization. Both the penalization factor are there in this factor. It's just like you are penalizing a lot more than the previous ones. And this is why people like this one more than the other two. But essentially, this comes from lasso and ridge combined. So we're going to do this now. When it comes to ElasticNet, we do it in a slightly different way. So you copy this code. Let's say elastic underscore net, or maybe just call it elastic. And we're going to have sale price tilde dot. You're going to have training data. Method is still glmnet. Training, this part is the same, but you don't need this in here. What you need is tune length. And we could just set it as some number of tunes you want to perform. I'm using 10 over here just to make it like faster. And yeah, I think this should be it about elastic. So you have to run the C first and then elastic. And this takes a while because it combines both of these. So, I mean, it's already completed. So it just takes a little bit more time. Let's actually compare these. And now we're going to create a variable called models, which is going to be a list of ridge. This ridge, that's the name of the list index. And I'm going to pass it the model ridge. So ridge equals ridge. So equals lasso. You know, let's just make this lowercase. And elastic. And now, so now I'm going to create resamples function that helps you find samples, and you want to summarize it. So actually now resamples modifies it, and then you want to summarize it. So for this, I'm going to use a library of tidyverse, because from that I can use what's called a pipe operator. So what this pipe operator does is, like, if you do modification and then you use pipe and you can specify another modification, pipe a third modification. So it kind of makes it easy to code if you have something really intense, because you don't have to always worry about doing a function inside another function, inside another function, inside another function, because that becomes really messy. The pipe operator makes it really easy to go about things like that. So summary, the pipe operator actually requires this package called dplyr, but this package is actually a part of tidyverse. So I usually just keep using tidyverse because it uses ggplot2 and all other sorts of things. And I already have it in my code, so I just use tidyverse instead of dplyr. So this summary, and I'll have to choose a metric. And this time we're going to choose RMSE, that's root mean square error. And since it is an error, you might want to minimize it. So I'm going to run models, I'm going to run resamples, and it is going to give me this list. And all it is going to give me the RMSE values for all observations across all these three models, and it's going to tell me the minimum, the first quantile, median, mean, everything you want to know. So how do you find the best model out of these? Is you minimize the RMSE, and most people either use the median or the mean to minimize it. I'm using mean in this case, and if you see, this is 329, this is 327. So elastic net model has the least RMSE, mean RMSE. That's why I would say the elastic net model is like the most is like the best one out of these three. And if you want, you could use median. If you use the median, you're gonna have bridge regression as the best one because it has the least median RMSE. So it really depends on your domain, what project you're doing, what metric you want to use, which one is better for your data, mean or median. This is about penalized regression, and I'm ending my regression part over here. So now we'll be continuing with classification. Okay, so let's move on to classification. And classification is similar to regression, but this time our dependent variable is going to be a categorical variable. So let's actually let me empty this environment because we'll be calling a lot of new models and things like that, and I don't want like the same names to be reused and we get confused. So let's actually import a data set for this. So it is an inbuilt data set about diabetes. Data, and the name of the data set is called Indians diabetes 2. It's from the package called bench. So see, this time it directly came in as a data frame, so we're good in this case. So we can do the STR where we see diabetes is a factor and it's like positive or negative. If it's 1, it means it's negative. If it's 2, it's positive. And then there's other variables that may affect a person having the diabetes or not. It's this mass, age, insulin, pressure, and a lot of variables. So over here, we can just look at it and say like diabetes is the dependent variable and everything else is probably the independent variable. And we see there's a lot of missing values, NAs in here. So what we need to do is remove those missing values just so that we can work on this pretty nicely. But in actual practice, it's not a good idea because this data set has a lot of missing values. You're gonna decrease the observations by a lot. Let's actually try that. Let's say Pima Indian diabetes $2 no, not dollar. Just say this thing equals the same thing, but we're going to put this into a function that is na.omit. So that removes all the NAs. Now, if you see, there is 768 observations and 9 variables right now, and when I run this, it becomes 392, almost halved. So it is not a good practice, but just for illustration purposes in this video, I'm doing this. And this data set name is too long. So if I wanted to write this thing dollar, let's say we want our independent variable diabetes. This is going to be too long, and typing this again and again is difficult. So let's do thing and course, if you're attaching to the end, you might want to detach. We're working over here in the middle, so let's attach. So let's again split it into training and testing data set, and we will copy our code from above. Gonna be this one. This is the method I usually use, but most people use the CA tools method most of the time. So this time we have, I think we don't need this daughter, we can directly write diabetes. And let's go with 0.8, which is the most common one here. And yeah, let's do the speed. This time we're actually getting an error. It says aims not found. So basically I just forgot to change the name of the data frame here. So now we'll have our training and testing data. Splits up pretty nice. And we can go for classification. So the first method is called logistic regression. And there's a lot of debate on why it's called regression, although it is classification. A lot of people don't like it being called regression. A lot of people say that it is a regression. And there is a whole debate, which I do not want to get into right now. So logistic regression works in a very similar way to the normal regression using the LM, but there's just a minor difference in there. So we'll create a model, and this time we are going to use a function called GLM. You see it's from the stats package, so it's already there by default, so there's no package required for that. And basically this is similar to the LM, so whatever you're filling in is going to be similar to the LM part. So this is diabetes. Tilde dot say data is train.data, and now we have another thing to add. It was family equals binomial. Now family equals binomial tells us that this diabetes is actually, so GLM is actually called global linear model, GLM. It's not specifically for logistic regression. You can do logistic regression, you can do normal regression using GLM as well, but you have to specify a family type that says this is normal regression, this is logistic regression. So binomials in this case means it is logistic regression. That's what it's telling the GLM function. So this is your model, and it works pretty much the same way as the others. We'll do summary of model. And so, okay, so binomial, it's starting from, and okay, here as well, summary. Summary model. You see there's a lot of summary we receive. This is logistic regression. And if you're not familiar with logistic regression, it's basically involving logs and things like that. So I'm not getting into the details, but basically we have a categorical variable, and we see the intercept is significant, the glucose is significant, mass is significant at 0.5, pedigree is significant at 0.01, and the others are not significant. So it is a pretty good model. It has a lot of more information given, the null deviance, residual deviance, and things like that. So this is one method, but we do not want to stop here. We actually want to find probabilities and check it with the testing data. So what we want to do is, so we'll find probabilities. So if you, the predictions. So first you'll have to find probabilities. Probability. Just a variable name, not a function. I'm then going to use the predict function we had before. From the model, I want to predict on test.data. And my type here is going to be response, because we're doing probabilities for a response variable. If you do predict, it's going to give us yes, no, yes, no, yes, no, things like that. We're not interested in that over here. We're interested in the probabilities, and probabilities is what we're going to approximate later on. So I'll run this code, and I'll run probabilities, and it's going to give me the probability of the model predicting that whether it is whether diabetes is like negative or positive. Now, how do you know which one's negative, which one's positive? For that, we'll have to use contrasts, because we're going to approximate that. So contrasts of diabetes. So negative is 0 and positive is 1. So if our probability over here, okay, so these probabilities here, what you're going to do is approximate it. If it's below 0.5, you're going to make it negative, because 0 is, because any number below 0.5 is in a regular fashion approximated to 0, the lower one, and 0 means negative. So that's how we'll do it. And if it is above 0.5, we're going to make it above or equal to 0.5. We're going to make it to 1. So basically for that, we'll have to use an if else function, which we saw before. So let's create a variable called predict. So predicted dot classes equals if else. Our condition will be probabilities is greater or equal 0.5. And if it is true, we're going to make it positive or else negative. And if you remember, this is how the data set had as positive, like NEG and POS. If I do predicted classes and then run predicted classes, I'm going to tell, oh, this is negative, this is positive. That's how you find it in most of the times using classifications. So once you have your predicted classes, now what you want to create is a table saying that the number of original negative versus the number of observed negative, predicted negative, and the number of predicted positive, but we're still negative. So we want to find like the false positives and false negatives. So for that, we'll have to create what's called a confusion matrix. If you don't know, it's just what I just described as like a table telling you the observed versus number of observed versus predicted. So that uses the caret thing and caret library, which we already did install. And he's gonna have this function called confusion matrix. And the thing with confusion matrix is you always have to factor everything you put in it. So we're going to factor predicted classes because that's the predicted ones we have, comma, the next one is going to be the actual ones. That's the factor of test.data underscore diabetes. And over here, you have to use the $sign even though we attached, because diabetes belongs to training data. It belongs to the original data as well as the test data. So if you write diabetes, they're not going to understand it. So, so yeah. And the last variable will be positive. Equals pos. So that just tells us that when the probability is greater than 0.5, which is when you're rounding it to 1, what is our actual outcome? Because if we put it as negative, we're going to get like the opposite of what we want. So by default, it's going to be negative. So you have to use positive equals this value every time you do it. So if you run this confusion matrix, it's going to give you a lot of statistics, and this is the table we need. So these are the predictions row-wise, and these are the original ones column-wise. So originally there were 44 plus 8, that is 52 negative diabetes people, out of which the prediction correctly classified 44 as negative, but 8 of them, they said it's positive, although they were negative. So this is the false positive range over here, this 8. And this 11 is, it was originally positive, but the prediction said it's negative, so that's like the false negative. And 15 is like the positive positive. That's like, so 44 plus 15, these are the correct predictions, and this 11 plus 8 are the incorrect predictions. And that's how you calculate the accuracy. It's like 44 plus 15 divided by the sum of all of these 4 numbers. So, and it also gives you 95% confidence interval. There's a lot of p-value and a lot of statistics. Usually people look at this p-value, the 95% confidence interval, accuracy, and these two, sensitivity and specificity. Those are what people usually look from confusion matrix statistics. So this is how you would do the confusion matrix for logistic regression. So now let's actually do stepwise regression and best variable subset regression for this classification. So the method of doing that is similar, but it's not exactly the same. So for stepwise, we'll have step equals from the mass, we're using this function called step PIC, which is the same one we used before. We're putting in this model, direction equals both. Until now, it is the same, even trace equals false. So there's one extra argument we need in here, which is k. So if you want to look at the documentation of this, we can do question mark step AIC and just find in k here. So k tells them the multiple of the number of degrees of freedom used in the penalty. Only k equals 2 gives you the genuine AIC. K equals log n is sometimes referred to as BIC or SBC. So it tells you different kind of metrics. And for logistic regression, there is a specific value for k that's supposed to be given, and that is actually the log of the number of rows of the data set. So this one, how do you find the number of rows of the data set? I mentioned in the beginning, it's going to be n row of the data set, and it's actually going to be the original data set, not the training or the testing set. And you have to take the log of this. So I'll put another parenthesis in here and then log. This is, let's put it in different lines so that it's more readable. So we run this, and then okay, there is okay ASS typo. Still says object mass not found. Oh, this is a. So yeah, now it works. And basically, all you have to do is run the step to get the information you need. So you have the IC value, the residual deviance, non-deviance, degrees of freedom, your final model, the logistic regression model. So this is how it works for stepwise regression. For best subset regression, say best subset classification. Here. So for this, we'll actually require a different library. The library is called STAT GLM. Let's run that. So now, basically, again, we're doing some something similar to cross-validation. So create CV data as a variable where you convert. This will be like model.matrix. So you're not converting your data frame into a matrix, but it's not the entire thing. And this one thing about this is you don't have to have a y variable because we are actually removing the y variable. And it's empty space tilde dot. Okay, model empty space comma dot, and then it's gonna have the data frame. That's this, the original data frame. And basically what I'm doing here is I'm going to do comma -1. So I'm basically removing this. After the comma is like the column space. So -1 means I'm removing the first column. If you see the first column is okay. It really depends. If you're not actually removing the first column, you're removing the last column. So the diabetes -1. So this will remove, if you see CV data, it has diabetes pause, and here does not have the diabetes. And it's now a matrix, not a data frame. That's why it does not have the blue one here. And basically CV data, I want to convert it to data frame in order to use it. So data.frame of CV data. So convert it to a data frame. And then you'll have best is basically the best model. This uses best GLM function from the best GLM library, and it's gonna have the CV data we had in here. Then IC is like the information criteria is the IC, that's what people usually use. And family equals by polynomial. That's it. This is telling them that it's logistic regression. And then we'll have best. So let's run this. We have this information here, so we got our model from the best subset classification as well. So this was all about logistic regression. Now let's talk about decision tree classification. There's another method of doing classification. So and we'll have a new data set for this case, and it's going to be the Titanic data set, which is also there in R, but a clean version is there in Categorical. So I'm going to import it from the Categorical, which I have it in my directory. This time I called it data. People call it data or DF or something like that. And that's actually not good practice, but because it's not clear, if someone's like looking at the script where there's a lot of data sets imported and they say a data set called data, they don't know it's referring to the Titanic data. But for illustration purposes, I'm just keeping it as data. And now basically, we saw na.omit, the method that uses to remove data, remove missing values. There's also another way of doing that, and that's data equals subset. So you just do a subset of the values that is not a null, not NA. So just put subset of data, and the condition is that it is not is.na. And we could just specify, I mean, since it is already clean enough, we'll just put another variable age. I mean, we haven't looked at what data is. Right now it has these columns, this passenger ID that is survived. So basically this is our dependent variable. Then we have the class first class, second class, third class, the name. Then there's a lot of information. There's age, gender, the ticket number, sibling, spouse, SP, sibling, spouse, the number of sibling and spouse. Person had parch. I don't remember what parch is. Fare is the fare they had for the ticket. Cabin, if they had a cabin or not. I mean, some of them are not there. There is embarked. So these are variables, and I'm just using age, although we don't have missing values right now. But this is just to show that we could do it this way. Basically, we can basically just do it for one variable if you want. You don't have to do any omit for the entire data frame at once. So yeah, this is how you do it. But this data set, it actually seems like there are variables that actually don't actually matter to us in this regression. I'm going to subset that out as well. So I'm going to do data equals subset again. And what I'm going to do is, again, it's going to be data, but this time I'm saying select equals minus of C, this is vector, with name, ticket, and cabin. Because the name of a person doesn't really affect whether they're going to survive or not. It doesn't depend on your name. So if you know variables that's actually not going to affect, you can remove them, start to write this. And this minus actually means that you're removing these variables from the data frame. So let's run this. If you see data, it has 12 variables right now, and if I run this, it's going to make them 9. So that's how you would do it. Now let's import libraries. There's 2 libraries we want to use for decision trees. You have to install them if you don't have it already. It's called, one of them is called rpart, and the other one is called rattle. So yeah, let's get started. First, let's split into testing and training, and we'll do copy code from previous parts. And this time, this is going to be survived. Okay. And this is going to be data. Let's stick with 0.8 as the splitting ratio. So yep, we have these. So first of all, let's have a look at data, the STR of data. Survived is actually an integer, but it's takes only 0 and 1, so we need to convert it into a factor. The way of doing that is we can do, so the thing is, if you want to, you have to convert the factor for training and testing data separately. You could have done that before splitting it. That would have been an easier task. Since we haven't done it, let's do it this way. So survived equals as that factor of the exact same thing. So the thing is, over here, you still have to use the data train.data dollar, because we haven't factored that. We have factored only the data. So we'll have to do this for test as well. Test data. So now we can get started making decision trees. So okay, let's make our model then. Model, now from the rpart package, we're going to call rpart function, and inside it's again similar to survive. It's similar to the lm function, so it's going to be survive tilde dot, and then data equals train.data, then no, but the thing is, this doesn't actually explain as of yet if the model is doing a decision tree or is doing something else. So for that, there is an argument called control, and it's going to be the value for it has to be our part dot control. This basically just tells that we're doing a decision tree. So it's going to be our part control of CP equals 0. That's what it means that we're doing a decision tree. We'll create this model, and basically it's a decision tree, so we want to visualize it, and we'll be visualizing it using the Rattle. And we use Rattle library we used, and fancy our part plot. And that is the name of the function. We'll just put in model, and yeah, we can just run it. So we have our model, and then we have this. So it gives us, let's actually try to make it bigger. Ex equals 0.5. Yes, it's a bit better. And this is how your tree looks like. So if you zoom in, so what I'm going to do is I'm going to run this over here so that I actually get in the plots one, and now I can zoom in. So this is how it looks like. And basically what this tells is, from this, there's a partition. If there's 0.6 and 0.4, if the probability is less than 0.5, it's a 0.6, it's a yes. If it's in the greater than 0.6, it's going to be no. And so the green ones is like 0, the blue ones is blue. So this is like 100% probability, this is 62% probability. So which means the blue ones are the ones people who survive, and the green ones are the ones who didn't survive. So this is a model, but obviously we have to make this better, like do the variable selection method for this to actually give us a shorter tree, a better tree. So I'm clearing this for now, and let's proceed with that. And now this time it's like a proper cross-validation method. So you have to train a cross-validation model. So we'll do set.c to 3. And what I'll do is, yeah, we convert to factors, so we should be good. So we can just create a model 2 now. So basically the function we'll be using is train, and so we have survived till the dot. Then we'll have data equals train dot data. Then method is still our part. Until now it is the same as what we did in the R part section. And we'll have TR control. This is similar to what we had before. So we train control from the car package, and we'll have CV in here, which means cross-validation, and again the tenfold cross-validation. Usually tenfold cross-validation is the most common one. A lot of people do fivefold as well. And then tune length is 100. So this is how you'll train your second model. I run this. Error in fail. Okay. We have an error in here, so let's run this part again. Part. Okay, error in na.fail default. It survived. There is missing values. So I believe, yeah, I think there is a problem with missing values in here. So let's try this. Yes, so apparently this data set had missing values. So now we can run our model 2. And of course, yeah, now we can just plot our new model, basically using this rattle and model 2. Okay, so there is an error in here. Okay, yes, since this is a cross-validation model, we'll have to use $final model, because we saw before, like when it's a cross-validation object, then it is difficult to actually get the model like that. And if you see this, this is more simpler. We can actually make this bigger. We can make it 0.9. This is very clear actually, so and a lot better, because you're training it with cross-validation. And again, the blue ones are 1, and like the darker the blue is, the more like the more deeper it is inside the graph, as well as more its percentage probability is. And the green ones is the people who did not survive. And basically, these are the conditions. So if sex male is greater than 0.5, then it's gonna be yes, and then otherwise it's gonna be no. So that's how we proceed. So this is how decision trees work. Now I want to go to the last classification I want to cover. There are many more classifications we can do, but I'm going to do the last one, which is called, maybe you might have heard of it, called random forest. And basically it is the same as a decision tree, but it is not one decision tree, but it's like a collection of decision trees. It computes several decision trees, and then it finds the optimal one from that. So a lot of people use random forest, and it is a very important concept. But yeah, it really depends on your domain that if you want to use random forest or not. So for random forest, we'll need a function, we'll need a library called random forest, and with the uppercase F in here, you have to install it. It's not there by default, like most of the other ones we used. And you can run this, and since we are having another model in here, we'll set .c. Then we'll just go with our model 3. It's similar to the previous one. It's like train, and a lot of it is going to be the same. So let me actually copy this one here. Model 3 will be survived dot data is trained dot data method. This time it becomes RF, that stands for random forest instead of rpart. Your TR control, it's again tenfold cross validation, and now you don't have a true length, but you have what's called importance equals true. That's actually not very important, but let it be there in here. And this will give us a model. Now we have to find predictions. So we will use the probabilities and predictions we had before. So probabilities will be predict model 3. So we test data, and we don't need the type equals response anymore. We don't need contrast because our categorical variables are survived is already zeros and ones. So it's pretty obvious which one is which. So now predicted classes will again be if else and probability. Now this time it's going to be equal to 1 because we're not getting our probabilities as probabilities, we're just getting it as zeros and ones because these are already zeros and ones, survived ones. So this is data. Let's actually pick up test the data because this one has survived as a factor, 0 and 1. So this we will have to make it to this thing equals 1, and this becomes 1, and this becomes 0. And we can run this. We predicted our classes. It's going to be a bunch of zeros and ones, and let's copy code from the previous matrix. And we have, I think it is pretty much the same code because we use the same variables. Diabetes changes to survived, and this changes to 1. And this should work. Here's our confusion matrix. We have 77 correct predicted as not survived, 33 correctly predicted as survived, 5 falsely, this is like a false positive, and this is like false negative. So accuracy is 0.7887, which is pretty much good. And random forest actually does work really good. And now what we want to do is we want to find like the best decision tree. So for that, there are 2 methods. There's one called mean decrease accuracy, and there's mean decrease Gini. And it really depends on the model we created, model 3. So we're going to use random forest. We're going to use where plot, which is a variance importance plot, and model 3 and model 3. And since this is already CV object, it's like a cross-validation object, we have to use final model. And we use type equals 1. Type equals 1 means that it is mean decrease accuracy. And if I copy the same thing down and change type equals to 2, and that's going to give us mean decrease Gini. These are 2 different ways of going about which one is optimal. So also, if you want, we can just okay, let's just run these first. So mean decrease accuracy, we have an error. Okay, so the second one seems to work. So basically what we have in here is mean decrease Gini, and it tells us the most important variable. Like, so sex male is actually our most important variable according to the mean decrease Gini metric, and then there's fair, then there's age, then there's passenger ID. If you check for mean decrease accuracy, apparently the code is not working for that. So I don't know what is the error about. It says subscript out of bounds. But if you cannot plot these, usually plotting this is not a very good idea, because if you see, it's not actually telling us what the mean decreased Gini is. And even if you know what the mean decreased Gini is, you don't know how it actually relates to our problem. So what most people usually do is we usually print out the percentages, and this uses the caret package. This function called var_imp, and you just type in model 3 type equals 1. The type equals 1 is basically meaning decrease accuracy, and type 2 is going to be mean decrease Gini. And okay, there's something wrong with our type equals 1, but when it comes to type equals 2, it'll tell you the percentage. Like the most important one is sex male. It's like 100% important, because like the first one, next one will be 68%, 52. It keeps decreasing until the last one. So that really helps you. And let's actually try to find out why this does not work. It says drop equals false. So let's try and drop. This is where the error comes in. If drop equals true, still doesn't work. So let's try to check if we missed something. So we did the probabilities, predict, test the data, predict to classified. Probabilities equals 1, 1, 0. We had our confusion matrix where we factored these. Should be good. Let's rerun this. It takes some time. These not work. So let's actually. So the random forest takes a lot of time because you're doing several decision trees again and again. So yeah, we need to wait. It takes some time to run. We need to wait. And yes, this time it does work. So yeah, let's actually plot them as well. So random forest import model 3 final model type plus 1. Let's see if it works. Drop. It does work without a drop. So 2. So for mean decrease accuracy, it's written at the bottom. This is the plot, and these are the percentages, even for mean decrease Gini. So this helps you choose variables. Of course, for your domain, there'll be a special benchmark for mean decrease Gini, like above this value, it is important, below that it's not important. So that's how you decide which variables to take in. So this is all about classification I wanted to cover. So now I'm done with the regression and classification I wanted to cover in this video. So thank you very much for listening and yeah, being there while I was solving my errors. So thank you very much for listening and watching this video.